Well, hello everybody. Welcome back to Astronomy, OpenStax chapter 12 today, talking about rings, moons, and Pluto. So let's get started right away. We're going to discuss the ring and moon systems in our solar system. We're going to talk about the Galilean moons of Jupiter, and then go over the moons of Saturn and Neptune, and then talk about Pluto and its moons, and the big one is Charon, but we've got a lot of other planets, so a lot of other moons around Jupiter, a lot of moons around Pluto, which might surprise you. And then we'll discuss the ring systems in our solar system. So thinking ahead, all of the giant planets have moons that orbit like planets orbit around our solar system, but the moons orbit the planets. So we can think of them as a miniature solar system, but not star-centric. Just like the moon orbits Earth, these other moons orbit other planets. There are more than 200 moons in our solar system, and we didn't know about a lot of them until we sent Voyager to the outer planets to take pictures of them. Because before Voyager, we didn't have the Hubble Space Telescope. We didn't have telescopes powerful enough to really view moons in detail or the planets themselves in detail, their surfaces. And then after Voyager spacecraft made it to the outer planets and took their tours, we were able to take pictures close up. And most of the pictures you're going to see today are from the Voyager mission. Not all, but most of them. Okay, so we're going to talk about the ring and moon systems first. So we want to be able to name, at the end of this, all the major moons of each of the Jovian planets. And by Jovian, we mean Jupiter and Saturn. And then describe the composition of each Jovian planet's ring system, okay? So this is Earth over here on the left side of your of the chart here. Earth's moon is right here. That's the only moon Earth has. Jupiter and its Galilean moons, we call them the Galilean moons because Galileo saw them with his telescope. Io, Europa, Ganymede, and Callisto. Those are the four biggest moons of Jupiter. You can see that they are all bigger than the moon except Europa, which is not much smaller than the moon. So they're all comparable size to our moon. And then Saturn, you can see it has a lot of little moons here, but its biggest one is Titan. And then Uranus has a bunch of little moons too. And then Neptune has its big one, Triton, which we'll talk about. And then Pluto has its moon, Charon. And then one of the dwarf planets, Eris, has its Dysnomia moon. So there's a lot of cool stuff out there. Jupiter, beyond those four Galilean moons, has 67 moons that we know of so far, of different sizes. They're smaller than the Galilean moons, but there's a lot of them. You could have a lot of mining stations on each of these moons, if you think about it in terms of a science fiction novel. Okay, there, Jupiter, you might be surprised to surprised to hear, does have a ring system. Okay, it has a faint ring, just like Saturn, but it's hard to see it. Saturn, on the other hand, has over 60 moons too, but it has a magnificent ring system. Oh, stunning ring system. We'll talk about the rings here at the end. Uranus, the outer planet here, has at least 27 moons, has its own ring system, as well as Neptune has at least 14 moons, and then its own ring system. The Saturn is the only one that's obvious, that's easy to see, but the other moons do have ring systems. They're usually a little bit darker. Okay, so the Galilean moons of Jupiter are pretty interesting. We want to understand the features that we can observe about Callisto, one of the big moons, and then what we can deduce from them. And we want to explain the evidence for tectonic and volcanic activity on Ganymede. We also want to explain what may be responsible for the features on Europa. It's actually a very icy planet. It's got an ocean under there. And we want to describe the major distinguishing features of Io, the pizza moon, as I call it. Okay, so Jupiter's Galilean moons, Io, Europa, Ganymede, Callisto. Here's Earth's moon to scale, as well as the planet Mercury, just to give you a sense of, so, the moons could be planets if they weren't orbiting Jupiter, for example. These are large moons or small planets. You could think of it that way. So the Galilean moons right here, and then we've included Titan here as a reference. But you can see that they're all compared to the mass of Earth's moon. So Callisto is 1.5 times the mass of the moon. Ganymede is 2 times. Europa is the only one that's smaller. Io is 1.2 times the mass of the moon, and Titan is about twice as massive. Another important property of a moon is its reflectivity. It tells you how much light gets reflected back out into space. That is a function of how much of the sunlight is absorbed to the planet to help keep it warm, for example. So here's Callisto. Look at Callisto. Look at all those craters on this. So not a lot of activity on Callisto. A lot of craters built up over time. It's the outermost of Jupiter's moons. It's way out there. You can see in the lab, the Jupiter lab we do, how far away Callisto is. It's unremarkable. It's a similar diameter to Mercury, but a third of the mass, so it's fluffy. It's an icy planet. Uh, uh, Ice here, when you're out this far from the sun, is as hard as rock. You really can't chip it. Kind of amazing. But by studying its gravity, we know that it is not fully differentiated. So it's not like Mercury, which has a very solid central core and an outer fluffy layer. Callisto is basically just a fluffy planet. It's not differentiated. It lacks the interior forces that drive the surface change. So we've talked about how on Earth you've got earthquakes and lava and volcanoes and erosion and everything that can change the surface. Callisto doesn't have any of that, so its surface is covered in craters and unchanged, basically. Ganymede, here's the moon Ganymede, another Voyager picture here. So Ganymede is Jupiter's largest moon. It's about a quarter of the surface, or about a quarter of it is as heavily cratered as Callisto, but that tells you that some of Ganymede has erased itself. The difference is Ganymede is actually close enough to Jupiter to experience what we call tidal forces. So it creates energy within the planet, which can drive lava and volcanoes and tectonic activity. Europa here is one of the icy moons of Jupiter. There's a movie called Europa Report. Check it out if you're into sci-fi. It's about folks that go there. There's an icy ocean under here, and the heat from Jupiter and the tidal forces that power a planet keep a liquid water ocean alive on Europa. So we're very interested to send a probe there, see the whales swim with the European dolphins if we can. It's also covered in a thick layer of ice. So this is, if Earth didn't have an atmosphere, this is what Earth would look like. It would be an icy world, covered in oceans, but the oceans would be frozen solid. The top of them, not deep in them. So this is the surface of Europa. These are the ocean areas that are frozen all over. I mean, it's really cool. See all these Santa's tracks from his sleigh, sliding around on the surface of Europa. And then we get to Io, which I call the pizza moon, because it looks a little bit like a slice of pizza. Maybe a disgusting old slice of pizza. Ugh. It's stinky. Smells like sulfur. It's a very stinky planet. It's a volcanic moon. Okay, you can see the actual volcanoes erupting and shooting stuff into space, which is kind of amazing. This is Io up close. You see the volcanoes flowing around here. Io is actually in what we call the hottest part of Jupiter. If you were to orbit Jupiter, there's an area where there's a lot of radiation, and Io is right there. So when Voyager flew into Io to take a picture, it got dosed a significant amount of radiation, higher than it expected, and NASA scientists had to deal with that when some of their protections for the spacecraft. It survived, and it continued taking great data as it flew to the outer solar system. So, tidal heating. Io, the pizza moon, is the most volcanically active thing in our solar system, besides the sun, which is just hot. So how does Io maintain all this heat 4.5 billion years after its form? How is it hot enough to keep pumping out lava onto its surface? And it's because Io is very close to Jupiter, and it doesn't have a nice steady orbit. It rotates, and so that means it's getting elongated and stretched, and then the whole planet is being whooshed like that, and it's like rubbing your hands together. It's going to generate some heat. So that same thing, the whole planet is just rubbing itself into a hot little ball. And the rocky planets get pushed and pull when they have this tidal forces on them, and it causes friction on the planetary scale, which generates a huge amount of heat. Okay, Titan and Triton. All right, so just to summarize that Io thing, the tidal heating is a main theme in the solar system, so just take that away from it. Rubbing things generates heat. All right, Titan and Triton. So we want to explain how the thick atmosphere of Titan makes liquid bodies of liquid on its surface possible. We'll talk about what type of liquid here in a bit, and then we can learn what we study what we learned when we landed a probe on Titan, and then we can discuss the features we observed when Voyager flew by. So this is Titan. Look at this moon. You can't see the surface of it. It's covered in a thick cloud. Isn't that cool? I mean, how cool is this? All these planets, moons, everything, all these diverse ecologies. So this is the surface of Titan here. You can see we went from visible light. You can't see the surface of it. It's that visible light. It's just a yellow methane ball. If you look with ultraviolet light, you can start to see the surface, but you see that it glows. The atmosphere is still glowing. If you look at infrared, you can see right through the clouds, right to the surface. And these are two infrared pictures that you can see through the surface. So that's a pretty cool picture when we take our spacecraft with all the different instruments, not just visible light, but infrared and UV and all these things. We can take this picture. So Titan is Saturn's largest moon. It has a thick, dense, nitrogen-rich atmosphere. Look at that thing. And then it's bigger than Earth's moon. You can see this to scale here. There are the pictures in UV there. The Huygens probe, it landed, it was part of the Cassini mission, which went to Saturn. So Titan is one of Saturn's moon. I'm not sure if I specified that or not. So Titan is the moon of Saturn. And Cassini was a space mission which went to Saturn and dropped off a probe on its way to Saturn, which landed on Huygens and took some pictures as it went down, as it landed. It revealed that Titan is a rocky planet. It's got little frozen rocks on it, organic compounds everywhere. This is a video. We're not going to watch the whole thing, but if you search the view from Huygens, you can watch this video, and it shows what the probe would have seen as it approached Titan, landed on it, and as it went through the clouds, the rocky valleys that it would have seen as it did it. And these are some of the pictures that it took here. You can see rivers and lakes, and they're actually made of liquid methane, and so it rains methane on Titan. So it's crazy. Okay, this is pretty awesome. This is a cutaway of what we've learned about the surface of Titan. Whole different world. Okay, Titan, where it rains methane, and then you've got that thick haze on its top surface, so you can't see through it. Now we move out to the outer planets, Uranus and Neptune, and here is the moon Triton. Okay, look at that beautiful Voyager picture of the moon Triton. It's Neptune's largest moon. It's about 75% rock and 25% water ice. The coldest surface in the solar system because it reflects about 80% of the light it receives. So look at this. It's a very light-colored moon. And so most of the sunlight that hits it gets reflected back out into space. So it's just very cold. It doesn't have an atmosphere. Okay. 35 Kelvin on its surface. Okay. 35 Kelvin. That's 35 degrees above absolute zero. Okay. So it's very, very close to zero. Like the coldest thing a thing can be. It's what we call a captured moon of Neptune. It's very similar to Pluto. So we imagine like a Kuiper Belt object came in maybe, or something in the asteroid belt went out. Don't know where exactly it came from yet, but probably from the Kuiper Belt. Okay, so it's very similar to Pluto. It has a cantaloupe-like surface. That's a clue to its activity. It's got pits of slushy ice on its surface. Okay, a little behind here. And it has cryovolcanic activity, which involves geysers of nitrogen. So we have Old Faithful here in the United States that shoots out steaming water. Well, imagine being on Triton and having it shoot out steamy nitrogen, okay? Because the ice is frozen solid. All right, so this is a picture. You've got some geyser action here. It's shadow shooting out from its surface. These little shadows everywhere. Pretty cool. Okay, getting to Pluto and its moon Charon. So we want to compare the orbital characteristics of Pluto with the other planets. Describe information about Pluto's surface that we deduced from the New Horizons spacecraft, which flew by. So Voyager did not visit Pluto, but New Horizons did. And in the last 5 years, we want to note some distinguishing characteristics of Pluto's largest moon. Okay, so there's Pluto. There's our first picture of Pluto. Isn't that great? Got the big heart here on its surface. Okay, loves us. First of all, what's a planet? Why isn't Pluto the 9th planet in our solar system anymore? So a planet is an object that has to be round. It has to be big enough that its gravity pulls itself into a round shape. Second, it has to not be orbiting anything else, and nothing else should be orbiting nearby it. Third, it has to orbit a star. So while we have some moons that are, bigger than the planet Mercury, they are not planets because they are orbiting Jupiter, for example. Pluto is a dwarf planet because it fails to meet the second criteria. It doesn't clear its orbit. It's not the only thing orbiting the sun in its vicinity. There are 5 dwarf planets at least in our solar system, and 4 reside beyond Neptune, so beyond Pluto, in what we call the Kuiper Belt, and that's Pluto, Haumea, Makemake, and Eris. Okay, and one of is in the main asteroid belt. Ceres is we thought for a long time the biggest asteroid in our solar system, but we've promoted it to a dwarf planet. Okay, so these are all, we got Ceres, which was the biggest asteroid, and now it's the one of the smallest dwarf planets. And you've got Vesta, and these other asteroids are what we call minor planets, so they're in the asteroid belt. Then we have Pluto, and you can see Eris and Makemake and Haumea, and then Sedna, Orcus, and then, so these are not all known to be, they're suspected dwarf planets. We haven't verified that yet, but we suspect them. They're so far away, it's so hard to determine. Okay, so those are what we call the dwarf planets, and that's what Pluto is. So Pluto was discovered in 1930, and you can see this picture of it here. That little red arrow is pointing at a little red dot, and then this one here, you can see that dot moved from there to there. So it moved from here to there. And that was how they discovered Pluto. Okay, it has 5 moons. It's about half the size of Pluto. Charon is the biggest one, which is half the size of Pluto. Here's a comparison. You got Earth here, you got Pluto there, and Pluto's moon, Charon. Okay, look at this. We got a picture of the Pluto. So they choreographed this whole thing as the spacecraft flew by. They knew that it would fly past it, like paparazzi, take pictures. They would come behind it, and then there would be an eclipse, and you'd be able to study the atmosphere of Pluto by doing that. So they turned the cameras around, took a picture, so you could really see how thick the atmosphere was by looking at the light from the sun going through it. And then we could see that, wow, Pluto does have an atmosphere. There's this haze here. So that's pretty awesome. Then we see all these icy mountains on the surface and these valleys here. Pretty amazing. It's got all this terrain here. Way more diverse than we expected to see. Way more alive than we expected to see. So Pluto looks like it's been pretty busy, actually. So we're trying to understand now how that's possible for something so far from the sun to be somewhat active. Okay, and then here's the largest moon, Charon. You can see it's not quite round. It's got a little bit lopsided. Something hit it pretty hard a long time ago. So you can see when things get smaller and smaller and smaller, they start to get less and less round, where the gravity is not strong enough to really pull itself in. The forces of the stone and rock kind of prevent that from happening. So it's pretty cool, though, that we were able to zoom in and fly by and see all these things. All right, so rings. We want to describe the theories of ring formation, and then compare the rings of Saturn and then how the moon Enceladus in the formation of the E-ring might play a role, and then explain how the rings of Uranus and Neptune are different, and then how moons affect the ring system. So Jupiter, Saturn, Uranus, and Neptune, they all have ring systems of different amounts. The reflectivity of Saturn's rings are the highest, and that's why we can see them. They're very bright. These are the ring systems and how far away from the surface of the planet the rings are. So Jupiter's rings pretty close to the surface, but there's kind of a limit here. And then Saturn is very thick. Look at that ring system, very far out. And then Uranus is pretty thin ring system. Same with Neptune, a couple of little ring areas. Okay, and then you've got the moons here orbiting. So we have this tidal stability limit, and that's where a moon can actually break apart because of the force of the tide, the force of gravity on the planet onto the moon is so strong. So look at this, Saturn's rings, so beautiful. You see these, there's a big carve out, big piece missing from the ring system. You've got the ring name, they have A, B, C, D, E, F, and so on. There's some of the width of the ring systems, hundreds of thousands of kilometers. Not hundreds, sorry, the outer edge, they stretch hundreds of thousands of kilometers out, but their widths are, thousands individually. And then here's the moon. This is my favorite. Enceladus, icy world around Saturn. You can see some more recent craters up here, but otherwise no craters down here. It's been erasing it. But my favorite is this. It looks like it's just shooting. Yeah, it's a rocket planet or a rocket moon flying around because it has those geysers, just like Io and Triton and so on. So you can see this Cassini image shows the water geysers shooting out into space. It's so cool. Salty water from the subsurface just shooting out into space. No atmosphere to really stop it. Okay, rings of Uranus and Neptune. Too dark to see from Earth, but with a high contrast image where you really wash it out, you can see, Voyager took this picture, you can see the long exposure, stars here or something else streaking across the image. And you can see the ring system of Uranus. It looks a lot like the ring system of Saturn, but it's not as reflective. And look at this, Neptune. You can barely see the planet, so washed out, but you see those two rings, a little more detail here. Okay, in Saturn's F ring, you can see these. Hey, look at this. How cool is this? You got a little moon here. You see these little ripples in the ring, and that's because of the gravity playing back and forth. Okay, and then you've got some moons here. So the ring systems, they're shepherded by some of the moons. So some of the moons around Saturn actually kind of herd the rings together. Sometimes they erase parts of the ring. Sometimes those moons break apart, and that dust becomes a ring. They orbit just like Kepler's law, so the more massive parts are a little bit further away. The lighter parts may be a little closer because they're traveling a little more quickly. I don't really know the masses of the different ring parts, but they follow the Kepler's laws in the same way. We call those shepherd moons the moons that are influence the ring shapes. Okay, and this is just a chart showing you where the ring systems are around the different planets. So Saturn is the most complex ring system. It's a very complicated system. It's got thousands of individual ringlets. Okay, and they all work together. Look at all these to make their things. So you got bright areas, dark areas. The dark areas may or may not have something there. They could just look dark because they're not made of the same bright material. So the gap's not necessarily empty. There could be things there in this dark region or that dark region that have material that's just not as bright. Okay. So Saturn's, they're bright because they're made of mostly water ice. Uranus and Neptune, darker than coal, so you can't really see them. They don't reflect the light. Jupiter's not as dark as the ice giants, but they're not as bright as Saturn's. Silicates made of things like that. You can also get, so two theories of ring formation is a moon, shoots volcanic material out into space, which gets trapped around the moon and orbits it, or a moon falls apart, gets crushed over time, cracks apart, breaks into smaller pieces, and that becomes a ring. The rings do not last forever. They break down just like patio furniture in the sun. Okay, they just evaporate. They break down. They break apart into little pieces. Shepherd moons help to stabilize the ring systems, but they will go away, and eventually Saturn will not have rings anymore, but it'll be a while. All right, Saturn's moon Tethys. This is one of my favorite moons. Look at this thing. It's been through some stuff. Okay, this is an example of a moon that's totally dead. You can't see a single spot on it that doesn't have craters. I mean, it's just been completely pulverized. Look at this. This is amazing. It's actually a Death Star. Okay, sorry. There's the Death Star. Mimus. Okay, that was a big impact right there. Okay, this is Ceres, a dwarf planet in the asteroid belt. This was Hubble's picture of it, and then we sent a spacecraft to it to check it out. That's it. Pretty cool, though. All the ring systems, all the different stuff in our solar system. Rings and things. All right, see you guys next time.